So I guess it can do both. Good. I always wondered about that. Wondered if it never finished it. All right, so let's start here and mark the time and start making a note of that. I will go to my share screen and get that going. Let me point out that this number 15, like really almost all the problems in here, requires us to think about what is the potential from a single point and then add up all the points involved in order to get the total potential. Okay. So I'll illustrate what I mean here and start off by saying, okay, so this is chapter 25, number 15, page 1. And if I go to the problem lists, number 15, it says here we've got these 3 charges in an equilateral triangle. And there's 4 centimeters on each of the sides. That's why it's called equilateral. And then the base is a little smaller at 2 centimeters. The charge at the top is Q, and each of the bases are the opposite at minus Q. I'll just remind you that minus Q doesn't necessarily mean negative. It means it's the opposite of whatever Q is. But as I read the problem, it says here 3 charges, particles are in the vertices of an isosceles triangle. Calculate the electric potential midway at the base, taking Q to be 7 microcoulombs. I'm going to write that as 7 times 10 to the minus 6. Okay. So we're trying to find it midway at the base. So here's the base, and that would be midway. But let me also make a vertical dotted line and point out that'd be straight down the center. And so that would be 90 degrees. But here is the idea of this chapter, that the total potential is the sum of the potential of the individual pieces that make it up. So the key to this problem, and really every problem here, is to know that the potential from a single point charge is given by this equation, KQ over R. And I think we were working on this one earlier, and I was trying to point out that this strategy of adding up a bunch of points is really the same thing we've been doing for the last 2 chapters. That is, of course, we're working with electric fields. All right, but if we knew the electric field from a single point, we could then add up all the points that are of interest. And in this case, I'll put capital N equal to 3 because we've got 3 charges. Each of them are going to make a potential at this point. So this would go from 1 to 3. If it was a continuous charge, then we would change the summation into an integration and say, well, let each point get smaller and smaller and smaller. So we would have a bunch of small points, and the potential of a small point would be K, and then we would have a dQ for a small amount of charge at that point. And we would have to add up then an infinite number of them. So we would be doing an integral. Now, that won't be necessary for this problem. We've just got 3 individual points. So we'll take this approach and go ahead and begin. So we've got Coulomb constant. And if I call this one in the lower left-hand corner number 1, its charge is minus Q, and its distance away from this point is 1 centimeter. I'll write it as 0.01 because Coulomb's constant is 9 times 10 to the 9th Newton meters squared over Coulomb squared. So we're going to want distances in meters and charge in coulombs. And so that's why when they gave it in microcoulombs, I put times 10 to the minus 6. All right, now if I go over to charge number 2, so I just go around in a counterclockwise direction, I would add up this one. Now this one is exactly the same as the other one. So I'm just going to double it. And then this will give me a chance to say, like I did earlier, is that, again, I think this chapter becomes a little easier. Notice I'm not saying easy than the other ones, because again, we're doing the same skills. We're adding up a bunch of points, but this time we're adding up a bunch of scalars. And when we did fields, we added a bunch of fields. When you add a bunch of fields, you got to not only know the magnitude, but you also have to mess with the direction. And that gets an added level of difficulty. Whereas here, we don't have a direction. These are all scalars. So it's the same distance away, it's the same charge, it's going to be the same number. So I can just double it. If these were electric field, I might say it's the same magnitude in opposite direction, so they cancel. All right. But that's not what we have here. We don't have them in a direction. So we just double it and into story. Now, the third one, the one at the top of the triangle, would be, again, Coulomb's constant. And instead of a negative Q, it would be a positive Q. And its distance away, we're going to have to do a little bit of algebra on. And so let me call that distance right here, say, X. And we already know this is 1. But we have a right triangle here where we would have something, maybe I'll put it up here at the top, 1 squared plus an x squared is equal to a 4 squared. Since this is the 4 is the hypotenuse, the x is one of the legs, and the 1 is the other leg. So that means x would be, that'd be a 16 minus 1. That would be the square root of 15. And grabbing a calculator here, the square root of 15 is about 3.87 centimeters. Now, putting it as meters then would be 0.0387. And maybe just to save a little bit of calculus or calculations, and so calculator work, the K and the Q can be factored out and multiplied at the end. So getting a number here, I would take a negative 2 divided by 0.01. I would add to it a 1 over 0.0387. And that would be this number here, a negative 174. Then multiplying it, going across this way by Q, that's 7 times 10 to the negative 6. And then finally multiplying it by Coulomb's constant, 9 times 10 to the 9th, we get a negative 1.103456 times 10 to the 7. And the units are worth looking at. Let's see, the unit for Coulomb's constant is a Newton meters squared over Coulomb squared. This charge here would be in coulombs. I did switch it up here to coulombs, okay? And this distance down here is in meters. And again, I purposely knew that to put it in meters, because then that would mean one of the meters on top with the one on the bottom would cancel. And then the coulomb on top with one of the ones on bottom would cancel. Then the top would have a Newton times a meter. That's a joule. And the definition of a volt is the energy per unit charge. So it is joules per coulomb. So a joule per coulomb is a volt. Just has the symbol capital V. So minus, if I move that, 11 million volts. Maybe 11.0 if I have 3 significant figures. All right. And yeah, so, and I checked this before that was the right answer, so I won't bother to check it again. So hope that helped.
Yeah, thank you very much.
Sure. Okay, so that's the strategy. Add up a bunch of points here. And in case you didn't catch it in the lecture, I'll say that, the reason we care about that potential is because then when you multiply by a charge, if you put it there, now that this problem didn't have us actually doing anything with it. This was kind of a step towards, why we care about it. But if we had put a charge here, let's just say there was like a 4 nanocoulomb charge that we were going to put in this place. Now that we know its potential, we would multiply by this 4 nanocoulombs of charge, and that would be the energy that would have. And then, of course, if we kind of let it go and it changed its position somewhere else, we can get the energy there, and then the change in energy would be equal then to the change in kinetic energy, and then we get how fast it's going. So that's one and useful reason that we like this. And in fact, if you don't see the parallel, let me point out, we did the same thing in mechanics in our Physics 121. We did things like forces and acceleration, Newton's second law. And we use forces to figure out how fast something would be going later, what its final speed would be. And so forces led to acceleration, and acceleration led to velocity. And we did that first, but then right after we did Newton's laws, and I think that was like chapters 5 and chapter 6 in Physics 121, we then jumped into 7 and 8, which was energy. And we did the same kind of thinking. How fast is it going? But we did a different technique. We did it with energy. So we're really trying to do the same thing here. In these first 2 chapters, we did electric fields, which lead to electric forces, which lead to accelerations, which lead to velocities. Here, we're dealing with energy. And that could also lead to velocities. And so this is our second technique to say, if we have a particle here and we release it, how fast is it going to get going? And so we're playing the same game, that we can either use forces, which involve acceleration and vectors, or we could use energy, which would involve conservation of energy, kinetic energy, and in this case, electrical energy, which comes from electric potential. So that's why we have this second technique. So this is paralleling that, exactly like we did with gravity. We have potential energy, we have electrical energy. And just like we did gravitational force, we have also electrical force. All right, well, let me switch back, because I think I see something else flashed into the chat here. All right, friends, so let's try number 67. Okay. And the time would be 3:17. So chapter 25, number 67. All right, so I'll put that here, and of course, jump back over and scan down for 67. So, this might be the second reason we care about potential. This would be a good lead into, let me read the question. So this might be a good lead into what I just said. Okay, so when an uncharged conducting sphere of radius A is placed at the origin of an XYZ coordinate system that lies in an initial uniform field E in the Z direction, the resulting electric potential is V naught for points inside the sphere, and this crazy thing for points outside the sphere, where V naught is a constant. Electric potential on the conductor. Use this equation, determine the X, Y, and Z components of the resulting electric field. Yeah, okay, so this is pretty mathematical, but before I jump into the mathematics, let me use this as an opportunity to continue to say what I was saying and then add to it, because there's 2 reasons we care about potential, and one of them is to get to the velocity. That's the one I said, and the other one is this one. So I like to draw this picture. If we're working with moving objects, we might want to know, say, their position. And there is a connection between their position and their velocity. And that's from Physics 121. If you take the derivative of the position, you get the velocity. If you integrate the velocity, you get the position. So if you know one, you know the other. Okay. Now, That being said, there's a mathematical connection between the velocity and the acceleration. Again, if you take the derivative of the velocity, you get acceleration. You integrate acceleration, you get velocity. So this is part of Physics 121. In fact, it's chapters 1, 2, 3, and 4 called kinematics of Physics 121, the connection between them. And also in parts of Physics 121, you could then get the net force, because net force equals ma. So again, if you know one, you know the other. And then net force is gotten from the sum of a bunch of individual forces. Yeah. Terrible picture here. Let me put it down here. Sum of all the individual forces. Okay. So again, this is what you learned in Physics 121. This was chapter 5 and 6, where you would learn about different forces. You would add them together to get the net force, which would give you the acceleration, which you would integrate to get velocity, which you would integrate to get position. So again, don't forget all this, but I would say this is why we cared about forces, so we can get velocity. But then also in Physics 121, chapter 7 and 8, we did this. We said that there was this concept of energy, and why do we care about it? Well, we care about it because if we apply conservation of energy, we can get the velocity through the kinetic energy in the conservation of energy term. We also said in chapter 8 that if you know the equation for the potential energy, you could take the derivative and get the force. Okay. Well, that's what I was saying in the last problem, or as I finished up the last problem, was that, why do we care about the potential? Because it leads to potential energy. So I'm going to put right above energy, potential. And the last problem, all we did was calculate the potential. But as I was trying to say, as I was wrapping up, even though it wasn't part of the problem, to kind of give you a bigger important picture, is if we were to put a charge there, so I'll call it the fourth charge. So these three charges made the potential, and then you put a fourth one there. You could then just simply, to get the energy, usually donated with U, taking charge number 4 and put it in the presence of the total potential that's made by the other three. And that's how you would get that energy. And then you would use conservation of energy. So the hard part of a problem like this is really getting the potential. That's why this problem number 15 we did before was exactly that. It would say, hey, add up all the charges, in this case, 3 of them, in order to get the potential. Had it been a more continuous problem, one that you care about in real life, not just kind of train you to get potentials, because that's where it stopped, because this was just trying to train you to get potentials, you would multiply by that force charge, you would get the energy, and then from the energy, using conservation of energy, you can get the speed after it moved. And so I was trying to say that's an important reason why we care about the potential. But I'm going to go and say, if you took then the derivative of the potential, watch this. And so adding to this chart, so drop the potential, this is the chart that represents Physics 121. What we've done so far is we've said right here, you can get to the net force from the net electric field, which you get from, and we had 2 methods here, either adding up the field from individual points, that was our first chapter, Coulomb's law, or you can get there using kind of a slightly tricky technique called Gauss's law. And so I would say that this step in this diagram right here is what we did in chapter 23. We learned the first method of getting an electric field by saying just take a bunch of points, the electric field from a point, add them up, you'll get the net. Once you do that, you just go Q times the net electric field to get net force, which will get you to velocity. So a lot of problems we did in chapter 23, we didn't do any more than this first step. We just said there were a bunch of points and got it to the field. But the reason we cared about it is because then if you put a charge where that field was, that'd give you the force. Force would give you the acceleration. You integrate the acceleration, you get the velocity. So that was a few times we went all the way to this spot. In fact, I think we integrated one more time and went to positions. But this diagram hopefully illustrates why we cared about that, even though we spent the majority of our time just doing problems like that, because it was kind of assumed you already remember this from 121 that, well, yeah, that'll give you force, that'll give you acceleration and velocity. And so the real point of it was to do this. And then also in the chapter 24, we did kind of this step. We said, hey, let me give you a different way than Coulomb's law to get the electric field. It's called Gauss's law. And so again, with the idea that most of the problems, all we did was do Gauss's law and stop at the electric field, but remembering that we hadn't forgot our physics 121. And so there were times that you were asked to then use that to find the force, to then find the acceleration, to then find the velocity, or even the position. So again, all of this part right here was physics 121. And so we spent most of our time last week with this step, and the week before that with this step. So now I'm going to point out that like physics 121, where we took the derivative of the energy, we got force. If we take derivative of the potential, we would get the electric field. And so I wanted to use this as an opportunity to kind of expand on what I said at the end of this first problem, which was, why do we care about the potential? Well, now I hope you can see in my diagram, there's two answers. We care about the potential for two reasons. Either A, we use the potential to get the energy and use conservation of energy to get velocity. That's one reason we care about the potential. But the other reason we care about the potential, it actually gives us a third technique of getting the electric field. And I say third because remember, we did Coulomb's law in chapter 23, we did Gauss's law in chapter 24, and now this doesn't have a fancy name, but the gradient of, or the derivative of the potential is the electric field. So that's where this problem starts. I hope I wasn't too long-winded here, probably was, but I wanted to say, just like in physics 121, so physics 121, we learned that the force in the x direction would be negative. The derivative with respect to x of the energy, potential energy, would give us the force in the x direction. Now, this is a funny looking derivative purposely, and what this means is take the derivative only with respect to x. It's called a partial derivative. Don't worry about y. If there's a y in the equation, which has to do, you might think of it as a variable, but since we're only talking about movement along the x-axis, this is saying treat anything that is not an x as a constant, and this is a variation along x. So it would give you the force along x. And then likewise, we learned that the force in the y direction was the same idea. I guess this is, again, part of chapter 8. This is part of this diagram right here, where I'm saying if you take the energy and you take the derivative, technically it's negative the derivative. And technically it's the derivative of each term. So that's referred to as the gradient, because you got to take a scalar and convert it into a vector. So these give you the components. And so usually in a physics 121 class, we don't do too much of this. And we kind of forget about it. We focus so much on energy and conservation of energy in this step that we don't often remember or point out that energy came from the integral over the force. So that means energy taking its derivative would be a way to get the force if you didn't know it. Usually we started with the force and integrated it to get energy and then use conservation of energy to get velocity. So, but we can go the other way around. So this way is integrating, this way is differentiating. And it's term by term. or I should say component by component. And so the three of these together is referred to as a gradient. So we're taking the gradient, we're taking the derivative 3 times, first x, then y, then z, to get the x, y, and z component. So that was a long way of saying that you may not have done much of this. So this problem could catch you off guard when it's saying find the electric field in the x direction. It's kind of my diagram, the step above. Instead of taking the gradient of the energy, we take the gradient of the potential. And instead of getting force, we get field. And you can see the difference. The difference between energy and potential is Q. And then back here, the difference between field and force is Q. So you go from here and just divide off the Q's on both sides and you get this upper line. So here's where I'm going to start this problem. Now that I spent a long time telling you, what was the second reason we care about it, is you're going to take the derivative of the potential with respect to x, take the negative of that, and you'll get the x component of the field. To get the y component, same thing. Take the derivative with respect to y and put a negative in front of it, and that'll give you the electric field in the y direction. And then to get the z component of the electric field, you would take the derivative of the potential with respect to z. And so that's this long discussion here. Take the gradient of the potential, and you'll get the electric field. And they're giving you a mathematical equation for the potential. They're not asking you to come up with it. That's actually a pretty hard one. This is an uncharged conducting sphere put in an electric field, and the potential is not easy to prove. So fortunately, they don't ask us to do that. That's probably something that will be asked of you when you transfer your next E&M class. This would be where you'll pick up, because it's about where we're going to leave off on this chapter. So for us, I'm just going to start this problem right here and say, all right, let's do the following. Do they ask for the field inside or outside of the sphere? For points outside the sphere, and V naught for the electric. Use this equation to determine the x, y, and z component of the resulting electric field. All right, so I think we've got to do both. I think we need to do inside, and that's going to be the easy one. So I'll do that first. So inside, to get the x component, we take negative the derivative with respect to x of the potential on the inside. Now, the potential on the inside, they say, is a constant V naught. Using our calculus, we know that taking the derivative of a constant results in 0. So we would say there's no x component to the electric field on the inside. Well, again, derivative of a constant is 0. There's no y component, and there is also no z component. So maybe that was so obvious we didn't have to write out the math, but I thought I would nonetheless. So if you're talking about inside the sphere, there is no electric field. The x component is 0, the y component is 0, and the z component is 0. In fact, we already knew that. That's what we did with Coulomb's law. We said that if you had a conductor, and even if you hollowed out the conductor, the charges would reside on the surface. And in the metal conductor itself, the field would be 0. But we also said in a cavity, in a completely enclosed metal container, the electric field would also be 0 inside the cavity. Now, we proved that using Gauss's law, but this one is also showing it because they give us the potential. Now, to be quite honest, it usually goes the other way around. Because we know the electric field is zero, we would know the potential is a constant inside the hollow part of this conductor. But I'm trying to point out that even if we hadn't done the last chapter, well, if I cross this out, even if we didn't know the electric field inside the cavity was zero, just taking the derivative of it would tell us that. Okay. So now, I guess I'll just call out page 2, and I'm not going to do much with it. Let's go to the real part of this problem, and that is to find the electric field. Let's see, how does it say here? The resulting electric potential equals, for outside, and it equals V as a function of X, Y, and Z, equals a V naught minus an E naught, that's electric field Z, plus a E naught and the A cubed, make that a little bigger. Yeah, A cubed Z. I better talk about A. I think A is the radius of this. I don't remember seeing an A in the problem. X squared, Y squared, Z squared to the 3/2. An uncharged conductor sphere of radius A. So yeah, so there it is. It was there. Of radius A is placed at the origin of an XYZ coordinate system that lies in an initially uniform field of E naught. So the field's uniform when we put this uncharged sphere in it. The resulting electric potential is, and they give this a crazy equation for points outside of the sphere, where V naught is a constant electric potential on the conductor. Use this equation. All right. So again, as I said earlier, trying to figure out that this is the potential outside is not simple. So we're not asked to do it. We're asked to do an easier part, which comes back to my page 1, which just says find the field by taking the gradient of the potential. So the electric field in the X direction would be minus the potential of, and if you don't let me, I'll save a little time and not write out all that. Because again, taking the derivative means anything that doesn't have an X in it needs to be treated as a constant, and the derivative of a constant goes to 0. So if I look at these 3 terms, the first one does not have an X in it. So that would be a 0 when I took its derivative. The second one does not have an X in it. I'll treat it as a constant. Now it changes with the vertical position. So if we were moving vertically in the Z direction, there would be some kind of field there. But as far as this way, there's no variation. So that one would be 0. And so we need to take the derivative of this. So this would be E naught A cubed, and we got to treat Z as a constant. And then think of this as X squared plus Y squared plus Z squared, and then think of it as in the numerator as negative 3/2 power. Oh, let me put the negative from that definition here. So we got the negative, and then we're going to take the derivative. And so all these are a constant. And then so I'm going to bring down the negative 3/2 from here. And when I do that, I've got to subtract 1 from the exponent. So this becomes now minus 5/2. Then I have to take the derivative of the inside piece, and that's a 2x. So it looks like the 2's would cancel and the negatives would cancel. And so we got E naught A cubed Z X 3. I think that's everything. E naught and Z. Okay, there's the 3. I'll put that in the bottom. And then there's the X. And so then this is over X squared plus Y squared plus Z squared to the 5/2 power. So that's the idea of this problem. And to remind you that my picture again, there's 2 reasons we care about the potential. We can either use that to get potential energy and conservation of energy to get velocity, or we can take its gradient and get the electric field. So that's what I'm doing here, taking the gradient. So let me do the Y component. Maybe I'll make the Y component a little easier on myself by saying, notice that it's essentially the same thing that I would do with the X. There is, the X down here and the Y are essentially the same. And it makes sense because remember, the electric field, and I'll put my fingers in the camera pointing up, is in the Z direction. And so you put this sphere in a field that's going up. And so it doesn't really matter how you orient the sphere. Find my standard sphere. Here's my foam baseball here. All right. So if you put the electric field, upward, then maybe across the blue line here is the x-axis and this is the y-axis. But if you were to twist it this way, the x and y kind of change on your grid, but yet the physics hasn't changed. So you kind of expect to get the same thing for the x as the y. It doesn't really matter how you orientate the x or the y. So it doesn't surprise me, and then looking at the math, it doesn't surprise me that it's essentially going to be the same thing. So these first 2 don't have a y in them. They would be 0. I would end up with this E naught A cubed and the Z across the top. Then, of course, when I took this derivative again, it would bring down a negative, canceling with the negative in the derivative part. So they would go away. I'd be left with a 3. The 2 is going to eventually cancel off with the chain rule. And the difference, though, being that I'm not there quite yet, but this would be the same. But the chain rule would have given me a 2y. The 2 still canceling with that 1/2, but there'd be a y there. So basically, I'm saying here, you take the answer you get for x, and you interchange x with y, you would get that answer. There is what we call a symmetry. Take it like this, take it like this. You can take what is an x and make it a y, and what is a y, make it an x, and you should come up with the same thing because there is no difference between the x and y axis. So sure enough, if I started here and everywhere I see an x, it becomes a y, so there's a y. And then this would become a y squared, but I'll put it here. And this would become an x squared, so I'll put it here. So the bottom wouldn't change, even though I'm changing x and y, I'd still get the same thing in the bottom. But this in the top, this x becomes a y. So that's probably the easiest way to do that derivative. It's just not do it again, but just replace x with y and y with x. Now, a harder one here is definitely the z. And so the electric field in the z direction is minus the derivative with respect to z of, and maybe I just better write this out, v naught minus e naught z plus e naught a cubed z. And I'm going to go ahead and put it at the top here, x squared plus y squared plus z squared to the negative 3/2 power. Okay, and so that is the given potential. So I need to take its derivative. So the first one's the easiest one. Again, it's a constant. So derivative of constant is 0. So that one goes. Second one's actually pretty easy too. The two negatives would cancel, and the derivative of the z would just be a 1. And so we're left with just E naught. And that makes sense because that's the original field before you put the sphere there. And then so the derivative of this is really how it has changed. That is, the original uniform field has changed because you put the sphere in its presence. And that's basically what we saw over here. Before we put the sphere in there, the field in the x direction and the y direction was 0. And so this term right here is how the field has changed because of the presence of the conductor. If the conductor wasn't there, the x and y z components would be 0. The potential would just be this equation without that. So this is the presence of the sphere. So of course, when we take the derivative, we expect to see this for the original electric field and then being affected. So let's see how it gets affected. I got to take the derivative of this thing. And I'll start by just saying there'd be a minus sign that would go right there. And it looks like I need to do a product rule because I've got a z times this thing. So I've got two things multiplied together to do a product rule. And I'll just put an E naught A cubed out in front and then do the product rule. So the product rule says take the first, so that's z, and multiply it by the derivative of the second. So that's minus 3/2. Then you subtract 1 from the exponent. And I'll move it downstairs at the same time. That would be 5/2. Write that down and subtracted 1. Then the chain rule would give me a 2z. Taking the derivative of the inside piece. So that's the first right here times the derivative of the second. And then plus the second, which I'll put it downstairs now. Times the derivative of the first. The derivative of the first is just z, so that's just a 1. And maybe do a little algebra here. So this would be E naught minus, and so we've got E naught A cubed. But I'm going to go ahead and get a common denominator of x squared plus y squared plus z squared to the 5/2 power. Because that's what I have over here. And I have that same thing if I multiply the top by x squared, y squared, and z squared. If I multiply by the top, I got to multiply by the bottom by the same thing. So that'll make a 5/2. So that's how I get the common denominator. And then notice then that a 2 would cancel off. And then this right here would be a negative 3z squared. Put together with a positive z makes a negative 2z squared. And then over here, we have just an x squared plus a y squared. So x squared plus y squared minus 2z squared over that. So again, this is the part that is the part that's saying the field has been affected by this amount. That's the original. So there's the z component. That's probably the harder one. And maybe just to check, swing over to the solutions here. Let's see. Oh, good. So your author does go to the inside first. So I'll come back to my page 2, and he goes, okay, inside, the fields are all 0. Okay. It's more interesting on the outside. So the outside, he's got a 3, an E naught, an A cubed, and X and a Z, and then he's got this in the top, but same thing. And then the Y, same, it should be the same, the 3, E naught, and you get a YZ, and he puts that one at the top. Okay, but the hard one, see if I did that one right, is the Z component. You would have this E naught, good. And then now I got a minus, he has a plus, but that's because he changed the sign here. So let me try that. Let me multiply this minus through here. So that would become a plus, and then we have a minus x squared minus y squared plus 2z squared. So he puts a plus E naught a cubed, and then he puts in this quantity. He's got a plus 2z squared, good, a minus an x squared, good, that matches. And then he's got this term, although he's got it up on the top because he's got to a negative power, but that's the same also. So perfect, check. All right, so that was maybe a little more of an exercise of mathematics and taking derivatives, but it was really more to keep you on your toes because we're not going to do too much of it, just like in 121. We didn't do too much taking the derivative of energy to get force. We're not going to take derivative of potential to get field too often, but more often than we did in 121. So to keep this part of the diagram in place, most of the time we'll just find the potential and stop there and realize that you are still remembering that the advantage of potential is it gets potential energy, which gets to velocity. So we will do this a number of times, but mostly we will just figure out what the potential is and stop, knowing that we can either go this way to get field or this way to get velocity. Good. Hope that helped. All right, well, let me jump back to the Zoom page here, my other screen here. All right. Good. All right. Can we do 62 and 34 if there's time? Oh. Yeah, I think, well, fine. What time we get done here? 4:30. Oh, well, we'll make it happen. All right, so number 25, let's go number 62. I'll put down the time of 3:52. And then put over here, okay, so chapter 25, number 62. And maybe I won't spend so much time kind of lecturing why we care about it and just jump right into the problem, make sure we have the time here. Oh, actually, yeah, this is not long, but not easy. Okay, so a solid sphere, keep that in mind. A solid sphere of radius r has a uniform charge density rho and total charge q. Derive an expression for the total electric potential energy. And then they make a suggestion. And I'll come to the suggestion because I'll follow the suggestion here. But I'm going to then go back to my last problem in this long-winded discussion about, well, how do we get to energy? Because this problem's asking about energy. And the answer is we take the potential, add it to the charge we place there, and that will be the energy. Okay, so keep that in mind because here's what they are suggesting. They're suggesting that you imagine, and I'll just put kind of a dotted line, that you start with empty space and then you start putting in charges. So you bring charges from far away, so way over here somewhere, and you bring them in and you stack them together until you get a sphere. Okay, so it would look something like this. Way over here is this little bit of charge, dq. I'm going to pick it up and put it, and I'll put the first one right at the center. And if I were to ask myself, how much energy did it take? I might do something like this. Now I'll start with the equation U equals to Q times the potential. But since we're talking about placing a small amount of charge, I probably should write it like calculus dq. So I'm taking a small amount of charge, dq, and I'm placing it where there's some potential. That would take a small amount of energy, du, because then I'm going to do it again. I'm going to take another small amount of charge, dq. And in this case, it might be actually a little more charge, because what I'm going to do is I'm going to, maybe in a different color, take this charge of dq and pack it in a shell, a spherical shell around the first one. And so now I get a little bigger charge, okay? Now again, if I wanted to know how much energy that took, I would take the charge I'm putting in here and the potential. Now, notice that the first charge I put in, there were no other charges around. So I would say that how much energy did it take for me to put the first charge in? 0. I mean, yes, it's a small charge, but it's a small charge times no potential. There's no other charges around. But this second charge, which I'll circle in green, when I put it in there, the charge is this number here, but I'm putting it in a potential that is created by that first charge that I put in there. Now watch this. I'll do this one in red, dq. So I'm going to take a third charge, and I'm going to pack it in also. And again, I'm going to pack it in the shape of a sphere around it. And again, you can see how this is going to be even more energy than the second one, because I'm putting a charge, and I think this would even be more charge, because even if I make it the same thickness, I spread out over a bigger radius. So I'm essentially putting in more charge the third time, although it's the limit as it gets thin. So it's really kind of an infinitesimal amount. So it's hard to say more or less, but I'm going to say more because it's just a bigger shell that I'm putting on it. And then look at this. The potential would be even much bigger for the third red charge, because the potential is now created by the first two that I put in there. Well, I'm going to do this one more time, and then I think you see the idea. I'll do it in purple. So let's take a fourth charge. So this fourth charge is going to be put here. And again, how much energy would that take? Well, again, this is our little bit of energy to bring in that charge. So I would have a dq in purple, which you might say is even a little more than number 3, which was more than 2, which was more than 1. All right. But not worrying about which one is more. The big thing is to be definitely more potential by far, because I say more potential because now the potential for number 4 is created by the totality of the 3. And then 5 would be the potential from the first 4. And the 6th charge I put in would be from the 5th, and then this would continue. So in terms of math, I would write it this way. I would say that the total energy needed to build up a charged sphere would be the integral of du, where du is this little formula right here. Du is how much energy did the first one, then the second, then the third, then the fourth, then the fifth, then the sixth, then the seventh, then the eighth. And then eventually an infinite number of them. So let me replace du with dq times v. All right. Now, here's where their suggestion is really nice. dq. Okay, well, let me come off to the side and say that this problem said that we had rho. Rho is the charge density. That means it is how much charge per volume. Now, the reason that's nice is I can then replace dq with rho dv. So this dq right here, I'm going to replace with rho dv, and then times v. Now, maybe I'm going to spell out volume, because I just noticed that I had a dv for volume, but I also have a v for potential, and that could confuse somebody. All right, so this is the infinitesimal volume of this packed spheres, these shells. And then this is the potential. All right, so let's talk about these two. This is the volume of each of these charges that I'm packing. Why don't I look at the purple one, since it's kind of the number 4, and you would pack around it. So if I were to take this sphere to represent the first 3, I guess that's blue, green, and red. They're packed together and they make this size. And then I come in with charge number 4. And charge number 4, I guess I'll use this piece of paper. I'm going to pack it all the way around here. Oh, what is the volume of this? And I think it's easier to see the volume once you take it off and straighten it out and say, okay, what's the volume of this piece of paper? And so it would be its length, its width, and its thickness. So its length and its width would be the surface area. So as I pack this in, the surface area would be 4 pi and whatever radius I'm at. So this is a variable that keeps getting bigger and bigger and bigger as I pack on this piece of paper, and then I'll pack on another piece of paper, and I'll pack on another piece of paper. And so the surface area is getting bigger and bigger. That's why I was saying it's probably getting more charges. I got a bigger surface area as I pack them on. Okay, so let's go back to this bottom one here. So if I unfold this, this would be the surface area, pi r squared, the surface area of a sphere. And then its thickness would be this calculus term, dr. How thick is this piece of paper? And we're having an infinitesimally thick, dr, 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 dr. Okay? So that right there is the volume. Now, this other V is the potential. And the potential would be what is formed by all the other charges that were added first. So again, if I'm thinking in my mind about this purple one, this right here would be the potential that's created by the other 3 before it, the blue, the green, and the red. So what is the potential of a spherical charge? Well, let me not go all the way through that, but your author did show that if you had a solid ball spherically charged, its potential would be the same as if all of that was at a point. And so it would be Coulomb's constant times Q over R, where then the R would be the radius of that ball. That would be the potential right at the surface. Again, the charges I'm talking about creating the potential are the blue, green, and red. And I'm packing on it the purple ones. The purple ones would go at a radius of the ball. So this would be the radius of the ball. This would then be Coulomb's constant. This then is all the charge that's been added so far to the ball. Okay. So I could then say something like this, that I'm just looking at their suggestion. Imagine the sphere as constructed of addition successful layers of concentric shells, which have a charge of this. Okay, so that's what I got. And I guess that's all the hint they gave. Okay. So let me do the potential. The potential would be K Q over R. And I need to be a little careful with this and say, okay, what is the meaning of this? Remember, this R, as I said earlier up here, this is the radius of the ball, but so is this R. So one of those R's are going to cancel off. That's good. Thing that might be a little tough here is this Q. This Q is not the total charge of the ball. This Q is only the charge that has been there while I packed on the first three, getting ready to pack on the fourth one. So this is going to be changing, and it would depend on what R is. So I need to give this some more thought about how is this related to this R. So I will. And I will do something that I did here. You see, here, I said the density was the charge on the shell divided by the volume of the shell. But I could also have done this. I could say that the density is also the whole charge Q divided by the whole volume. And I will tell you that's not very useful, but it's true. What's going to be useful for me is I can think of the density as a charge that is represented by the first three layers, as long as I divide it by the volume of the first three layers. So notice I used a little r, because the first three layers only has a radius of little r. So if I use the whole charge, I got to use the whole radius. But if I use part of the charge, I can use partly of the radius. Just like I can do a little bit of charge over a little bit of volume, a little bit of charge over a little bit of volume, all the charge over all the volume. Okay, so that would be an important step, because now I can do this. All right, so right here, I've got this rho. And I've got this 4 pi, and I'm left with an r dr here. I've got the Coulomb's constant from here, already canceled that r. And then this q is what I was talking about right there. So this would be a rho times a 4/3 pi r cubed. And now the only variable is that little r, and everything else is a constant. So let me pull out what I can. There's 2 rhos. There's also 2 4 pi's. There's a Coulomb's constant. There's a 1/3. I think that's it, right? There would be an r to the 4th and then a dr. So let me just double check. So there's density squared. I go a 4 pi and a 4 pi. Coulomb's constant and a 1/3. Okay. And then an r cubed with an r, and then just a dr. And now we're going to add it up from 0 to r. So this would be rho squared, 4 pi squared, Coulomb's constant over 3. And this would make the integral of this would be r to the 5th over 5, evaluated from 0 to capital R. And this would be capital R to the 5th over 5. Now, I probably shouldn't stop there. I've done the hard work, if you will. But there is, I'm going to open my window. It's warm in my place. All right. Maybe I should look at the answer, but a lot of times the general rule is to put the answer in the symbols they gave us, and density was, well, I guess they did give us density, but I could change density of total charge, because if I come back to this page, you can see that density squared would be related here to total charge squared. And so I might take advantage of that, but I'll tell you what, before I do, let me see what the author does for an answer, because I know that I wanted to know if there was enough time to do the other one. And it looks like your author keeps going here. So I'm going to too. So let me replace density squared right here with q squared over. And so this would be a 4 pi squared. This 3 would come upstairs, 4 pi squared, and then we would have r to the 6th power. I think that's right. So density squared, I got a q squared, and this comes up there, so 3 squared, good. 4 pi squared, good, and r cubed squared. Okay, so that's density squared. Then there's a 4 pi squared right there. There's Coulomb's constant. There's a 3, there's a 5, and there's an r to the 5th. So what's nice about this is that the 4 pi squareds cancel off. One of the 3's cancel off. A lot of the r's cancel off. And so it looks like I'm going to have on the top a 3 and a 5 on the bottom, a 3 and a 5. Also down on the bottom, I'm going to have an r. I'm going to have a Coulomb's constant here, and I'm going to have a q squared. I think that's it, q squared, yeah. And that matches with the author. Nice. Nice. All right. So calculus wasn't too hard, but the whole concept of packing on charges on top of each other, and the energy, I think, is. And then that's why we result in some calculus. And then again, one of my favorite phrases, to do this, you got to make sure you're understanding what each term means. You're reading the math, not just doing the math, because these were big steps that you've got to, I mean, actually, considering how long it took me and all the talking I did, there's really not that many mathematical steps, but understanding what the volume is, the density, how I manipulated the density 3 different times. This would be the density thinking about a little shell. This is the density of a little ball. This is the density of a full ball. And I took advantage of those 3 times in order to get to here. And so that density can play a tricky role. So again, I'll say the same thing. We saw this same technique in the other 2 chapters. So in some sense, I think this is an easier chapter, but you can see that's not easy. So these are not easy problems, but the skill you've seen before. Maybe you didn't fully understand it. So I get that. And so hopefully seeing it a second time, third time, fourth time, but not the 5th time. And it finally sinks in. So that's, I guess, why this is a good problem. All right. Well, that did take longer than I thought it would take. But the other one was, and number 34, if you can. Okay. So number 34, and it is 416. And so I'll put here chapter 25, number 34. It took me about 25 minutes. So let's see, but I'll make sure I do it, even if it takes over the time. And let's see what this one is. So number 34. 34 says this: consider a ring of radius capital R and total charge Q, spread uniformly on its perimeter. What is the potential difference between the point at the center of the ring and a point on the axis that is 2 radius from the center? Okay. Now, I think then the author wants us to just say, what is the change in the potential? And we can then take the potential at the final minus the potential at the initial. And since this is a ring, let's find the potential of a ring. Now, at the fear of talking too much, let me show you how to get the potential of a ring. It's a nice review, but it was done as one of the examples, and I will pull back to it because I want to say it was example number 5. There's 4. Yeah, and there's 5. So 5 says, find the potential of a ring, and it comes out with this: Coulomb's constant times the charge on the ring divided by the square root of a squared plus x squared, where if this is the ring, x is the distance along the axis outward, and a is the radius of the ring. Now, that won't take long to derive, so I'm going to go ahead and derive it real quick and then put this down here to actually do the problem. But here's the important part of this chapter, that in order to figure out the potential of some shaped object, a ring, a rod, a sphere, a shell, a cylinder, you want to just add up the potential from a bunch of points. And if it's a continuous object, like a ring, I'm going to imagine chopping the ring into really tiny pieces. And no matter how much you imagine how tiny they are, go even smaller, go even tiny, so that eventually you end up with an infinite number of points that are infinitely small. Okay, so infinitesimally sized points. Because what that would mean is we would change this summation into an integration. So instead of adding up, say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, looks like I did about 20 points. So instead of adding up about 20 of these, I'm going to add up an infinite number. And I need to know the potential from a point charge. And the potential from a point charge was KQ over R. And if the really, really small point charge, we can just replace the Q with a DQ. And R is the distance away. So for a ring, this actually becomes pretty easy because the R, the distance away for the charges at the top of the ring, are the same at the bottom of the ring, which are the same at the side of the ring, left side or right side, because it's kind of a cone shape. So what's really nice about this integral is R is the same value for all the charges on the ring. In fact, not only is it the same value, I can use Pythagorean's theorem to figure it out, because this would be X and then this would be A. And so this distance here would be X squared plus A squared square rooted. So this R is then the square root of X squared plus A squared. So there's the R. And then this integral is even easier. This gives me a chance to say, again, don't actually do the integral. Think about what it means. Now that I've factored this out, this actually says not add up the potentials, but now this says add up the charges. And if you add up DQ, you're eventually going to add up all the DQs. You're eventually going to get the total on the ring, which let me call that capital Q. So that's why your book has this formula here. They went through these steps here in example number 5. Now, I think for this problem, you don't have to derive the potential from a ring. You could start with it, because the problem is actually the potential difference between 2 points from a ring. So I think the author is intending for you to start with what he derived, the potential from a ring, and then take that difference. But I thought I would take a few moments, because I think we have the time, in order to show you again the ideas behind adding up a bunch of points and getting the potential from a ring. So I'll say it again. I got the potential from a ring by adding up a bunch of points. It was an infinite number, so I turned it to an integral. And fortunately, this integral was an easy one because R didn't change. And then the integral of dq is just the total charge. All right, so knowing that, I'm going to come back here and say the change in potential then would be this equation, KQ and its final position minus its initial. I need to go back to the problem here. It says, let's see, what is the potential difference between the point at the center of the ring and the point on its axis, a distance of 2r? Now, they don't really say which way it's moved from. They don't really say if we're going to be moving from the center of the ring out, or we're already out and we're moving in. So it's hard to really know which one they mean final, but I'm going to take it in the order they gave. They say center. So I'm going to call the center the initial, and the point it moves to the final. So it moves along the x-axis. So starting with this idea of final, I would have KQ, I would have these square roots. Now remember, they gave us a squared for the radius, but in this problem, they're saying the ring has a radius of capital R. So maybe this is a chance to say again, don't just do the math, read the math. Because we need to see that the A that we derived for the ring, or that the author derived for the ring, wherever you get the potential for the ring, was the radius of the ring. And we called it A in our derivation. But in this problem, they have now changed that to capital R. We need to recognize that. So that's why I'm going to quickly take this formula that says A squared and change it to R squared plus. Now, if I take final, because they say move to a point on the radius that is 2r, my x would be 2r squared. Okay, so there's the final. That would be the potential at this point right here. Now, initial would be at the center of the ring. And at the center of the ring, x would be 0. So using this formula, this would be kq over the square root of, and I'll say it again, a is the radius of the ring, so that'd be r squared, plus, and this x, and so initial, this would be the center of the ring, so that'd be a 0 squared. All right, so this would be a kq. If you look at this, this would be 4r squared added to this makes 5r squared at square root. And minus kq, and then this would be the square root of r squared. And I suppose one more step, simplify it. And even went a little faster than I thought. We got a few minutes before our end time here. Let's see, I've got a k and a q that can factor out. And if you look here, the square root of r squared is just r. So I can factor out an r. And if I do that, this first one would be left with 1 over the square root of 5. And this would be left with a 1. And I'll have to look at the answer. I know in math, they don't like radicals on the bottom. So let me first get a common denominator. And then let me multiply by root 5, top and bottom. So the bottom becomes a 5. And then this becomes root 5 minus 5. And so they rationalize the denominator. And that's kind of old school thinking. If you ever wondered why they don't like it, it's because the old slide rulers needed to divide by, or helped to divide by an integer. So no decimals, no fractions, no irrational numbers there. And so we'd always rationalize the denominator in the slide rule days. But that's kind of irrelevant, I think, in today's world with our calculator. So I have a feeling that the author might have stopped there, although common denominator is nice, so maybe there. But then also rationalize the denominator is kind of common. So I'm going to take a look at what your author did for the solution to, what was it, 34? 34. Oh, and actually your author does one better. He says, put this into our calculator and get a number. All right, so I guess I could do that one, or that one. But since I did this one, I'll go ahead and take the square root of 5 minus 5 for the numerator and divide that by 5 and get a negative 0.553 kq over r. And that's how your author puts it at the end. And actually, I like that a lot better. I should have just done that back here. In fact, I think I will. 1 divided by the square root. 1 divided by the square root of 5. And then minus 1. Yeah, same number. Okay, good. Yay! All right. Hey. And unless there's another one I should address here, this might be a good stopping point. With my Zoom. Zoom. Oops, that's not it. Other Zoom. Ah, good. And Brendan, I think we got it. Although it looks like Brendan, you might have had to leave, so you're gone. But Johnny's still here.
Well, yeah, I appreciate it. So thank you.
All right. Well, hopefully it will serve him and hopefully many others
Yeah,
really
exactly.
well. When I finally process the video, and I'll probably do that in a couple hours from now. I need a little break, but
Yeah, definitely.
yeah. All right.
Okay. Thank you so much. I
All right.
really helpful.
Take care.